Hi, y'all. We have a few problems to get through that we didn't have time for the other night. I got a couple of problems from section 7.1 where we verify the identity. And we got 4 trig equations that we need to solve. Let's jump right in. First, this is number 7. Sorry, it's number 9 from the 7.1 worksheet. We want to verify the given identity. Now this initially looks like it might be easier to do a right-hand side to left-hand side type of situation. Let's get my skinny marker back. All right, so we're going to maybe start with our right-hand side and see what we can make out of it, because looking at this, it looks like we can FOIL some things out, and that might get us somewhere. So let's see what that looks like. 1 minus. Did I get the skinny marker back like I wanted? Yeah. All right. I guess I'm just pressing down too hard. There we go. 1 minus sine t cosine t times sine t plus cosine t. If I FOIL this out, that will be sine t. That's my first. My outside would be plus cosine t. My inside is minus sine squared t cosine t. And my last will be minus sine t cosine squared t. Now, that didn't look like it got us too far, but what I see is I've got a sine squared and a cosine squared that I might be able to work with. But before we work with it, let's see if we can't. Let's see, I've got two terms that involve a cosine t, and I've got 2 terms that involve a sine t. I'm going to group those together. So let's get my sine t terms first. I got a sine t minus sine t cosine squared t. Those are my sine terms that I have. And then my cosine terms, we have a cosine t minus sine squared t cosine t. Now we can factor out a sine t here. Got sine t times 1 minus cosine squared t. And we can factor out a cosine t in the second group. Cosine t times 1 minus sine squared t. And then I've got 2 expressions here. 1 minus cosine t and 1 minus sine t. That, all right, we can do something with those. Remember, we have this Pythagorean identity, cosine squared. Well, usually it's sine squared plus cosine squared is equal to 1. And so we can rearrange this to say, well, the 1 minus cosine t is sine squared t. And the 1 minus sine squared t is cosine squared t. And we get what we need, sine cubed t plus cosine cubed t, which is where we want it to end. All right, so our right-hand side to left-hand side argument worked. Now, that required a little bit of vision. That required a little bit of vision in terms of identifying, 2 terms that had signs, or sorry, those weren't the right terms. 2 terms that have sine t's and 2 terms that have cosine t's, so that we could kind of get things factored out. And there are other ways that we could have proceeded. For instance, you could have, instead of being clever and grouping things together, you could have just turned this this sine squared t into 1 minus cosine squared t. Let's see what that would have looked like. All right, so here's my initial proof. Let's get rid of all this stuff and see maybe if we weren't clever enough to see how we might be able to group these things together. Let's just convert the sine squared and cosine squared kind of where they are. Sine t plus cosine t minus 1 minus cosine squared t times cosine t minus sine t times 1 minus sine squared t. So I just converted this sine squared into 1 minus cosine squared, and this cosine squared into 1 minus sine squared. When you FOIL things out and be careful about minus signs, then you get minus cosine t, right? Minus 1 times cosine t. This is supposed to be a plus right here. Minus 1 times cosine t and minus a negative, which makes a positive, cosine cubed t. And then I get minus sine t minus a negative sine cubed t. And now we get some things that cancel. Sine t and minus sine t, cosine t and minus cosine t. And so we have cosine cubed t plus sine cubed t, which was essentially what we were supposed to get anyways. By the way, if you don't write down the next step using the commutative property of addition, I'm not gonna split hairs for that. So that's another way to have gotten the job done. And the second way is less about seeing that something's going to work, and then maybe you don't see a path forward, but you get your hands dirty and say, well, I know I can play around with sine squareds and cosine squareds. Let's do that and see where it leads. And it just so happened that it led us down the right path. So don't be afraid to get your hands dirty. Now, there is actually a more clever way to get this problem done, and it's going to require that you remember some factoring formulas that you were meant to have mastered in 136. In particular, the sum of cubes formula. A cubed plus b cubed is a plus b times a squared minus ab plus b squared. So that's the sum of cubes formula. There are a few ways to remember that, but that's something you're supposed to learn in 136, and I'm reminding you that you knew that in 136, and now you can go relearn that. However you learned it for 136, go relearn that. But here, it looks like if instead of doing a right-hand side to left-hand side thing, if we just start with our left-hand side, that's a sum of cubes. Sine cubed plus cosine cubed. That should be, let's see here, sine of t plus cosine of t. That's the a plus b part. And then sine squared t minus sine t cosine t plus cosine squared t. That's applying our sum of cubes formula. And then in that second bit, I have a sine squared plus a cosine squared that I can use my Pythagorean identity and say, oh, that's 1. Sine t plus cosine t times 1 minus sine t cosine t. Hey, that's exactly what we were supposed to get on our right-hand side. So this is like a two-step problem. Again, if you don't use the commutativity of multiplication to write the next line, I'm not going to... I guess here's one example where you don't actually have to... Well, I don't know. Just to be safe, I suppose you should. Make it look like the actual right-hand side, but I'm not going to worry about something that basic. So there's a lot of different paths that we could have taken through this. I think this last one is the shortest and neatest, but it's also one that might be more challenging to see. So I guess the point here, I wanted to show you that just to, hey, there's these sum of cubes and difference in cubes formulas. We did some factoring of cubics by grouping in class, but there's also a couple of factoring formulas that you can use for some cubics. So don't forget those. On to the next problem, another verify the identity problem. In this case, our right-hand side is 1, and there's not a whole lot of, I suppose we could start off with, all right, 1 is equal to sine squared plus cosine squared. Sorry, sine squared theta plus cosine squared theta. But then moving from there, it might be hard to see how to move from there. We'll be able to reconstruct something like that once we get to the end here. This actually, if we start with the left-hand side, which it seems like that's the one that has the most promise to be able to work with, the left-hand side here is actually a perfect square trinomial. So we're getting to, in the last couple of, between some of the equations that we solve, as well as some of these trig identities, we're getting to remember some facts about factoring. We're getting to practice our factoring skills so that we don't lose those for later. The perfect square trinomial is basically, if you take a binomial and square it, you get a squared plus 2ab plus b squared. So this, the right-hand side here, is the perfect square trinomial, and our left-hand side here has exactly that form. Oops, this is supposed to be cosine to the 4th. Where a is sine squared theta and b is cosine squared theta. So we can factor this into a plus b sine squared theta plus cosine squared theta squared. No, hey, there's a Pythagorean identity. That's 1 squared, and 1 squared is 1. So recognizing that as a perfect square trinomial, again, makes this one nice and short and quick. So if you remember factoring things, these last couple problems are pretty straightforward. But if you didn't remember those factoring things, let's see what we can do. Sine to the 4th theta plus 2 sine squared theta cosine squared theta plus cosine to the 4th theta. Well, I can call the first term sine squared theta squared. The middle term I'm not going to do much with. And I guess the challenge here is we're going to use the Pythagorean identity, but it might be hard to see where we should use it. I'm going to go ahead and leave cosine to the 4th theta alone out here. I'm going to turn this sine squared theta into 1 minus cosine squared theta using the Pythagorean identity. And I'm just going to go ahead and leave everything out here alone. So when I FOIL out this term, I get 1 minus 2 cosine squared theta plus cosine to the 4th theta and now I'm a little bit worried that this isn't going to work out, but that's okay. That's okay. We're getting our hands dirty and seeing what we can make of this. This is what getting our hands dirty looks like. We're not always certain of what the end result looks like. All right, and so using some ideas that we used before, I've got a couple of terms that involve cosine squareds that I might be able to combine, and see some cosine to the 4th terms that I can combine. So the cosine squared terms, there is, I'm just going to go ahead and do this. 1 plus 2 sine squared theta cosine squared theta minus 2 cosine squared theta. And that way I can put those in parentheses and group them together. And then I got 2 cosine to the 4th thetas. In this middle group with the parentheses, I can factor out a cosine squared theta. I guess that's the point. And I can factor out a 2 as well. Since I had cosine squared thetas, I kind of grouped them together so I could factor them out. And I'm left with sine squared theta minus 1. And there's some more sine squared thetas that I can turn into cosine squared thetas if I wanted to. Now, it turns out that, all right, well, I'll let you go ahead. I'll leave it up to you if you don't believe me here. Prove the following identity. This is close enough to an actual identity for me, but that sine squared theta minus 1 is negative cosine squared theta. It's the Pythagorean identity. It's like one step away from a Pythagorean identity. So I'm not worried about you using that fact immediately. But if you don't believe that fact, go prove it. Go prove it quickly to yourself. And then now I have 1 minus 2 cosine to the 4th theta plus 2 cosine to the 4th theta. And my cosine to the 4th thetas cancel, and I just have 1 left. So, all right, that path worked. Not recognizing the thing that we started with as a perfect square trinomial. We can still make something happen. This is a perfect example where I just said, hey, there's a sine squared playing with this sine of the 4th, and we can make something happen there. And there's other things that you can try too. There's all kinds of, like, we could have turned this sine squared into cosine squared theta and saw where that led us. So there's lots and lots of different things to try. The point is, don't just sit there and try to guess what the right step is. There is no right step. There are a bunch of correct steps, meaning there are a lot of things that you can do that are correct. You can write sine to the 4th theta as sine squared squared. That is correct. That is a thing that you can do. So there are a lot of correct things that you can do. And the point is, if you don't see what to do, just do something that's correct and see where it leads you. You know, put one foot in front of the other. Even if you accidentally go in the wrong direction, you can always step back. The point is like, don't jump in a hole. Don't do something wrong algebraically or use an identity that's not a correct identity to try to force something to happen. All right? So, but don't be afraid to just try something and see where it leads you. That's one of the very important skills that you learn in math classes, hopefully, that you're meant to. It's a lot of times you don't learn those things because you're pressed for time to get the right answer right away, but you're supposed to learn how to get comfortable with just trying something. All right, moving on to the 7.2 questions. We have a few here. We want to find solutions. And number 15 from the worksheets, I want to find all solutions to 2 sine v cosecant v minus cosecant v is equal to 4 sine v plus 2. Was that supposed to be plus 2? I think it's supposed to be plus 2 or minus 2. Where's my notes? Obviously, there's not supposed to be 2 equal signs there. Minus 2. Minus 2. All right. Now I've got sines and cosecants. Actually, this one we can factor by grouping. I didn't think about that. Let's do that real quick. Let's see what that looks like. 2 sine v. If I get everything on one side, cosecant v minus cosecant v minus 4 sine v plus 2 is equal to 0. In my first group, I can factor out a cosecant v. I got cosecant v times 2 sine v minus 1. In my second group, I can factor out a negative 2. And I'm left with 2 sine v minus 1. So we can factor this by grouping. I didn't even consider that until just a second ago. All right, so we have a fully factored trigonometric equation. We can use the zero factor property to say, well, either 2 sine v minus 1 is 0, or cosecant v minus 2 is 0. We got a product of two things is 0. One of those things must be 0. Here we get sine v is 1/2. Here we get cosecant v is 2, which is the same as sine of v is 1/2, right? So they're really the same equation. They're really the same equation. So we don't need to actually solve this one. This is redundant. All right, when we solve sine v is 1/2, there are two values. We're looking for just the values in 0 to 2 pi. There's two places where sine is positive, one in the first quadrant and one in the second quadrant. And one of the ways that I kind of remember my trig, like I know the values. I know the values for these trig involve 1/2, root 2 over 2, and root 3 over 2. And those are increasing in value. And so if I want sine to be 1/2, sine is the y-coordinate. I want these shallow angles as opposed to the steeper angles. So that's how I kind of think of my unit circle. I know what my value, I know what these values are, and I know how they rank in order. And so I know that I'm looking for the shallow angle, which is pi over 6. And then over here it has the same reference angle, so it's pi minus pi over 6. I said pi over 6 and I wrote pi over 2. That would be pi minus pi over 6 is 5 pi over 6. So those are my two solutions here. Because again, we were just looking for these solutions in 0 to 2 pi. All right, now the way that I initially saw to solve this equation, go ahead and erase it. It's nice when it's on the video that I can erase things because you all can just rewind and pause as opposed to the alternative. My initial thoughts when I saw this equation was just to turn all the cosecants into 1 over sine. We can use a reciprocal identity. So 2 sine v times 1 over sine v minus 1 over sine v is equal to 4 sine v minus 2. And then we have kind of a rational equation. If I multiply everywhere by sine v, I can get rid of those fractions. Actually, here they cancel. Let's get 2 minus, when I multiply, oh crap. Let's take this a little bit. Let's take this a little bit more slowly. Let's not multiply by sine v just yet. Here, this is 2 minus 1 over sine v is equal to 4 sine v minus 2. Now I'll multiply on both sides of this equation by sine of v to get rid of this denominator here. And I'll get 2 sine v minus 1 is equal to 4 sine squared v minus 2 sine v. And if I bring everything over to the left-hand side so I can keep my coefficient on the sine squared v term to be positive, I get 4 sine squared v minus 4 sine v plus 1 is equal to 0. And this is a perfect square trinomial. This is, I guess I'll write it. This is 2 sine v squared minus 2 times 2 sine v plus 1 squared. So this factors into 2 sine v minus 1 squared. And so that's where you would get your 2 sine v minus 1 is equal to 0. And the rest works out as before. So that would be another strategy. That was, again, that was my initial thought. That was my initial thought when I saw this. And as I would, right before I started, I'm like, wait a minute, this I think is going to factor nicely if we factor by grouping. And it did. So all of these factoring skills that you learned in 136, keep those things kind of in your back pocket. You want that stuff right there whenever you're solving any kind of equation. You want all that stuff right there in your back pockets. You want to always consciously be kind of looking, peeking here and there to see if it shows up. It's not something that you stare at for 5 minutes, but you're like, hey, is this a perfect square trinomial? No, move on. Hey, is this something? Are there 4 terms here? Can I factor this by grouping? Maybe, maybe not. No? Okay, I'll move on. But that kind of stuff, that's how you kind of start to get good at these things. Number 16 from our worksheets, find all solutions. Now we don't have to work. Now we actually have to find all solutions, not just the ones in 0 to 2 pi. All right, now this one's already factored. And so we could say sine of 2x is equal to 0, or cosecant of 2x minus 2 is equal to 0. But sine can't be 0 at the same time as this happens. Or if sine is 0, then cosecant is undefined. All right, let me write that here. If sine of 2x is 0, then cosecant of 2x is undefined. Right? Because cosecant of 2x would be the reciprocal of sine of 2x, which would be 1 over 0, which, all right, as soon as we write down 1 over 0, we quickly erase things and go, wait a minute, that's not supposed to happen. All right? So, yes, this equation has solutions. But no solutions in the domain. All right? So I think I mentioned in class that when you have a pair of trig functions, there are always these domain issues that you need to be aware of. Especially, anytime secant, cosecant, tangent, and cotangent show up in an equation, you have to be aware of the domain issues. All right. So we'll just go ahead and solve this equation now, because no matter what happens with cosecant, sine is fine. Sine and cosine are fine with all numbers. There are no domain issues with sine and cosine. So no matter what we find for cosecant, we'll be able to get the job done. So we have cosecant of 2x is equal to 2. It's cosecant, not cosine. And that means that sine of 2x will be 1/2. Now if you need to make a substitution, say sine of u is 1/2, where u is equal to 2x, so that you can not focus on the 2x part so quickly. Then you would get that, let's see, 2x would need to be, 2x or u would need to be pi over 6 plus 2 pi n. Remember, we're finding all the solutions. Or we would get 2x is 5 pi over 6 plus 2 pi n. This is the same. Sine is equal to 1/2 is the same thing that we just got done doing. I think we saw last night that these numbers just keep coming up over and over and over again. So if you haven't gotten to a point, if you're doing these problems and you haven't gotten to a point where you're constantly going, didn't I just do this one? You haven't done enough problems yet. Then here we're trying to solve for x, so we'll just divide by 2 on both sides and get pi over 12 plus pi n. Remember, we have to divide the period term by 2 as well. Or over here, we get x is 5 pi over 12 plus pi n. And that would be all the solutions to that equation look like that. 5 pi over 12. On to 17, find all solutions. Now here's one where we can maybe get some of the job done without pushing symbols. Sine of x is equal to cosine of x. And rather than thinking about where does a trig function equal a number, we can think of where are these two trig functions equal. And you can look at your unit circle. Right? Where is the x coordinate? That's the cosine. Where is the x coordinate equal to the y coordinate? And you will see on your unit circle that is at pi over 4 in the first quadrant. And it also happens in the third quadrant at 5 pi over 4. Right, so rather than looking to see where a trig function equals a number, here we can just look and see where are the trig functions equal, where are the coordinates the same. Now, if you didn't want to do it that way, you could have jumped to, well, divide on both sides to tangent. You could see where does tangent x equal to 1. But still there, the way that we've been thinking about where is tangent equal to 1, we're thinking about where are sine and cosine the same. But if you start to build your new unit circle, I'm not going to make this, well, we'll go ahead and make the first quadrant where you could say there's pi over 3. I'm not going to label the angles just because we know what the angles are. The points here are, 1, 0, 1, 0, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, 1/2, root 3 over 2, and then 0, 1. And if you, like we talked about the other night, if you want to write down the sines and cosines and tangent, like the sine and cosine are the x and y value. Or sorry, cosine and sine. Cosine is the x value, and sine is the y value. And then if you want tangent, you could just do the ratio of sine over cosine, or y over x. Tangent, maybe I should say t here. Tangent t is 1/2 divided by root 3 over 2, which is 1 over root 3, which is root 3 over 3. So there's the value for tangent there. Here, tangent of t is 1, root 2 over 2, root 2 over 2. Here, tangent of t is root 3 over 2 divided by 1/2, which is just root 3. And here, tangent of t, well, that would be 1 over 0, but all right, as soon as we write down 1 over 0, we should quickly erase it and say, instead, undefined. If you wanted to say cotangent of t is equal to 1 here, that's fine too. I don't know why I made these t's opposite of what I normally make them. All right. But yeah, it's not necessarily a bad idea to start to fill in some of the values for tangent and maybe even cotangent as well. It might be a little bit overkill talking about secant and cosecant, but that's not necessarily a bad idea either. But make sure that you got that unit circle down. Like, so you almost want it to be a point where you can visualize it in your head as opposed to having to write it on the page. But if you have to write it on the page, that's fine too. Moving along, this is the last one, I think. Find all solutions to this equation. Sine of x plus cosine of x times cotangent of x is equal to cosecant of x. I think we should just write everything in terms of sines and cosines right off the bat. Cosine of x times cosine x over sine x is equal to 1 over sine x. And then, well, there's a few things that we could try, but we could multiply on both sides here by sine of x just to clear out denominators, and then I would get sine squared x plus cosine squared x is equal to 1, and that's true for all x. Every value is a solution. So you're tempted to say, all right, our solution set is all real numbers. That's kind of it's called Blackboard Bold R, is the symbol used to denote all real numbers. In interval notation, this would be minus infinity to infinity. But then remember, there was some domain issues. All right, we started off with sines and denominators, and so our solution set to the original equation is not all real numbers. Our solution set is something else. All right, so we would need to. All right, so the bad numbers would be solutions to sine of x is equal to 0. That would be x is equal to some multiple of pi. 0, pi, 2 pi, 3 pi. That's where sine of x is 0. And we want to throw these away. And usually the way that we would denote throwing them away would be r throw away the set of and pi or something along those lines. Now, I don't know if you guys are going to run across too many problems where we have to worry about, all right, how do I denote the solution set? How do I talk about removing a bunch of points from the real line? So let's not concern ourselves with that too much. Let's just think about the idea of, well, I got to take my real number line and just throw away a bunch of distinct points. Now that brings up another point here, is that the original equation is true for all x in the domain. All right, the only points that we had to throw away from R were the points that weren't in the domain. So this is an identity. This is an identity. All right? And so if we want to prove that it's an identity, let's just go ahead and do that real quick. It starts off in much the same manner. Sine x plus cosine x cotangent x will be sine x plus cosine x times cosine x over sine x. And we get a common denominator now. We would get sine squared x over sine x plus cosine squared x over sine x. And now add those fractions together, get sine squared plus cosine squared on top, and the rest is pretty straightforward. I feel like maybe we did one of these. We did one just like this, I feel. Or maybe I'm misremembering. So that's 1 over sine x, which is cosecant x. Right, so that's how we would prove that that's an identity. So I don't remember. I must have I must have intentionally put this problem on our list. Actually, I grabbed a bunch of problems from another trig class that I taught and put those on our list. So I'm guessing I intentionally put this one on there just to drive home the idea of what an identity is. But this one ended up being an identity. So those are all the problems that I wanted to go through. If you have any questions about any of these problems, send me an email or a message on IvyLearn. Otherwise, I'll see y'all next time.